This is problem number 19 on page 311. Y double prime minus y prime minus 2y equals to 5 sine x. And the initial conditions are y at 0 equals to 1, y prime at 0 equals to negative 1. Alright, we're going to solve it by Laplace transform method. So when I take the Laplace transform of the entire equation, I get L of y double prime minus L of y prime minus 2L of y. I can factor the 2 out because it's a linear operator. Equals to 5 times the L of sine x. Okay, well, again, we're going to turn this into an algebra problem. And I need to, because I don't have it memorized, I need to look up what L double prime is. And so let's see, where is that? L of y double prime is s squared L of y minus y prime at 0 and then minus s y at 0. I'm going to take a little shortcut here. I'm going to let L represent L of y, just to save us some writing. And so that's what I did there. Now the minus L of y prime, and y prime, when I subtract L of y prime, I get plus y at 0, and then minus SL of y, SL of y, which I'm just going to write as SL. Okay, yep, that's good. And then minus 2L from right here, minus 2L equals to 5 times Laplace transform of sine x, and I want to make sure I get that right. So I go back to my table, and sine of 1 times x would be 1 over s squared plus 1. So it's really a 5, because we're multiplying by 5. So this equals to 5 over, make sure I get it right, s squared plus 1. There we go. So let's solve for L, and we have the L terms are s squared, this term, and minus s, this term, minus 2, times L of y, which I'm just writing as y. So I picked up the this term. Let me mark them off here. Picked up this term and that term and that term. And you'll notice that s squared minus s minus 2 really comes from the characteristic equation of the differential equation. I don't think that's going to be a coincidence. All right, minus y prime at 0, that's negative 1. So it's minus negative 1 plus minus s times y at 0 minus s times 1 plus 1 equals to 5 over s squared plus 1. So let's see what we got here. I've got s squared minus s minus 2 times L plus 1 plus 1, 2 minus s equals to 5 over s squared plus 1. So I'm going to subtract this term and then divide by this term, and that gives us L is equal to 5 over s squared plus 1 minus 2 plus s, and then all this is divided by s squared minus s minus 2. There we go. So, and remember, you know, L is L of y. So the solution y will be the inverse Laplace transform of this big mess here. Now that is a mess. That is a mess, and I think we can probably do some cleanup here. If first of all, I'm going to write this as 5 over s squared plus 1, and plus s minus 2. I sort of see something coming here. So I made this s minus 2, separated it. The bottom factors as s plus 1 times s minus 2. So I think that's going to be convenient to work with. Alright, well, I got to do some erasing here. I took this one down here, and this term is 5 over s squared plus 1 times s plus 1 times s minus 2. And then split up this term in here, the s minus 2 is canceled, so the right hand is just 1 over s plus 1. So that's the easy one. This will be a mess. And to handle this, we're going to need to split it up by using partial fractions. So it's a little bit of a challenge. I'm going to walk you through it. Now, the book has a lot of stuff on partial fractions in a previous lesson, and you can also learn quite a bit about partial fractions from calculus books. So let me erase this and I'll walk you through this one. I'm only concentrating on this for the moment. 5 over s squared plus 1 times s plus 2 times s minus 2. And I want to break up these factors into different fractions using those factors. I'm not going to worry about factoring s squared plus 1. It will with complex numbers, but let's don't go that far. Now, this term is second degree down here. So it turns out, in setting this up for partial fractions, I need to do a first degree polynomial on top. So the first degree would be as plus b. These are all first degrees, and that's why we're using constants, because the numerator is 1 degree less than the denominator. So that's how you do this type of partial fraction. Now, when I clear the fractions, I'm going to multiply by this denominator. It's going to clear all the fractions. And we get a big mess. 5 equals to as plus b times these two factors, s plus 1, s minus 2, and then plus c times these two factors, s squared plus 1, s minus 2, plus d times these two factors, s squared plus 1 times s plus 1. There we go. So, one thing we could do is to multiply all that mess out and equate the coefficients. And if you did, you'd find that we have a third degree polynomial in s on the right hand side. And so a third degree polynomial on the left hand side would be 0s cubed plus 0s squared plus 0s plus 5. And we have 4 letters to solve for in a third degree polynomial, a, b, c, and d. So all that's going to work out rather nicely. If you've played with partial fractions before, with complicated ones, you know how easy it is to mess this part up and get something that you can't solve. But I think I'll use the other technique, which is to let s be really nice numbers. For example, if s is equal to minus 1, then this term is 0, and this term is 0, but the c term is alright. So if I plug in negative 1, and here I've got 5 equals to negative 1 squared is 1, 1 plus 1 is 2, 2 times negative 3 is negative 6, minus 6c. So, yep. So that makes c equal to, I'll write it up here, c is equal to minus 5/6. Okay, well that's good to know. Now then, so we tried negative 1. Let's try positive 2. When s is equal to positive 2, then this term cancels off, and that term cancels off, but the d term is there. So we have 5 is equal to d times 2 squared plus 1 is 5, and then 2 plus 1 is 3. So I have d equal to 1/3. Okay, so d equals to 1/3. Alright, now how are we going to get A and B out of this? Well, I could, I suppose, let S equal to I, imaginary number I squared plus 1 is -1, that will cancel this term and this term. That would work. Oh, we try it that way. This is kind of novel. So if I let S be equal to imaginary number I, then I have 5 is equal to AI plus B times I plus 1 times I minus 2. Ooh, I'm not sure I like the looks of that. And then that's going to be 0, that's going to be 0. Now I still have 2 letters to solve for here. So I could work with S equal to minus I, plug that in, because minus I squared is still I squared, which is -1, which cancels the positive 1. So letting S be minus I will cancel the C and D terms. So here we have 5 equals to minus AI plus B times minus I plus 1 times minus I minus 2. Alright, well, I'm not sure that's all that fantastic here. What other alternatives do we have besides using those numbers? Well, we could plug in D and C and then work with it that way. Well, we could try some other things. You know, suppose that we let S be equal to 0. If S was equal to 0, we would have a number here, a number there, and if S was 0, we would have A would disappear, and B would be a number. So rather than try to sort through this, we can work this, but that just seems to be too complicated. So let's try a different approach. Let me try this other approach I have in mind. If S equals to 0, 5 will equal to 0A plus B, so I have B times 1 times -2 plus C minus 5/6 times 1 times -2, and then plus D, D is 1/3 times 1 times 1. There we go. So we collect up all these terms here. 5 equals to minus 2B plus 5/3. Okay, the 2 cancels, the negative cancels, leaving 5/3 plus 1/3. Oh, that's not too bad, is it? Because 5/3 plus 1/3 is equal to 6/3, or 2. If I subtract 2, I have 3 equals to -2B, so B is minus 3/2. There we go. B is minus 3/2. So now we have to figure out what A is. What in the world is A? I think I'll just let S be equal to 1, because we know what everything else is except for A. So if S is equal to 1, I think we'll get some nice friendly numbers here. 5 will equal to AS, so that's S. Oh, I'm sorry, S is 1, so it's A plus B, A minus 3/2, times, plug 1s in, I get 2 times 1 minus 2 is -1, plus C, C is minus 5/6. When I plug 1 in, I get 2 times -1, right? And then when I plug in 1 here, I get D, which is 1/3, plus 1/3 times 2 times 2. Okay, you know, I probably could just erase all this stuff up here. So, no, I gotta be careful. I gotta be careful in my erasing, because I'm gonna need some of this stuff, aren't I? Alright, well, I'm gonna take a chance and erase this. equals to negative 2 times a minus 3/2 plus 5/3 plus 4/3. Oh, and that isn't that convenient, because 5/3 plus 4/3 is 9/3, or 3. That's 3. If I subtract, I get 2. So let me erase here. I subtract this 3, so 2 equals to negative 2, parentheses a minus 3/2. If I divide by negative 2, I've got minus 1 equals to a minus 3/2. So a would equal to minus 1 plus 3/2, which is 1/2. So a is equal to 1/2. All right. Well, now I think we can write out our Laplace problem here. I had to scrap the last part of that video the first time through because I managed to plug the wrong number in over here, and it ended up being a mess. So I'm going to try this again. So I recopied the board, and here's all the information we have up to this point. Now, I'm now going to solve for the Laplace transform of y, Ly. And it's going to be this part plus 1 over s plus 1. So I have as plus b. That would be 1/2 s minus 3/2 over s squared plus 1. And then c is minus 5/6, so it's plus negative 5/6 over s plus 1. d is 1/3 plus 1/3 over s minus 2. And then we have plus 1 over s plus 1. So, let's see. When all the dust settles here, I have a... we can factor out a 1/2 here. So I have 1/2 times... on top we have s minus 3 over s squared plus 1. And then over here, I have these two terms combined, so I have 1 and then minus 5/6 makes a positive 1/6, so plus 1/6 times 1 over s plus 1, and then 1/3 times 1 over s minus 2. Okay, now let's look at the Laplace transform table on page 306 if you have this book. And I think these are very straightforward. Yeah, this is going to be an e to a power. That's going to be an e to a power. This one, I don't think we have quite this one. This is looks like both a sine and cosine form. So I need to split this up a little bit further. So I'm going to do a little racing up here. I took this stuff on the bottom here, and this is a fraction I broke up. So I have the 1/2 s over s squared plus 1, and then minus 3 times, oops, a little error there. It's actually minus 3/2, isn't it? Minus 3/2, because the 1/2 times the negative 3. 1 over s squared plus 1, and then these two terms I just recopied. Alright, well, let's erase this, and we need to look up these in the Laplace transform table, because now we can solve for y by taking the inverse operator, L inverse. And because it's a linear operator, I can literally spread the inverse operator across all these terms. And so technically it looks like this. I think this is a step you wouldn't normally write, but y would be 1/2 L inverse operating on s over s squared plus 1 minus 3/2 L inverse operating on 1 over s squared plus 1 plus 1/6 L inverse operating on, I'll use that bracket notation, 1 over s plus 1 plus plus 1/3, L inverse operating on 1 over s minus 2. Like I said, I don't think you really need to write that step, but I wanted just to show it to you to kind of reinforce everything I've been talking about. And so what is L inverse s over s squared plus 1? Well, if you look at the cosine AX column, a row in this table, where a equals to 1, because we have s squared plus 1 squared, then this is literally the cosine of x. So y would equal to 1/2 cosine of x. And then if you go right above it, a equals to 1 over s squared plus 1 squared. That corresponds to the sine of 1x, or sine2ax. So this translates to minus 3/2 sine x. And then, go 2 lines above that, the 1 over s minus a form. Well, a would be -1 here. S minus -1, of course, would be s plus 1. So when a is -1, then this inverse transform becomes e to the minus ax, or minus e to the negative x. So I have minus 1/6 e to the negative x. And then finally, here a equals to 2. This is going to be 1/3 e to the 2x. So there we go. That's hopefully the correct answer to this problem, and now I'm going to cross my fingers and check it. And I forgot what problem this was, but it looks like it's probably problem 19. Y equals to 1/3 e to the 2x, check, plus 1/6, e to the minus, and look what I did here. That should be a plus, shouldn't it? So please fix your notes, that's a plus, and you probably saw that. So that should be a plus. Alright, 1/6 e to the minus x, okay, minus 3/2 sine x, and then plus 1/2 cosine x. So it looks like they have what I have written in reverse order, but it's the same answer. So that's a relief. That was kind of a big one. So anyway, that's as you can see, these Laplace transform problems are in a way algebra problems, and but the algebra can be kind of tedious when you have these big partial fraction expansions. But okay, hopefully this was a pretty good example of all those facets.